There are a lot of cool things you can do with Blender's shader nodes. Some things are so impressive that coming up with something yourself appears to be impossible when you're a beginner. But most of the time, you just have to cleverly combine very basic setups to create something great. Think of it how in reality, rather simple things are used in very different ways to create so many different things. For example, the most famous invention, the wheel, is rather simple to understand, but its properties are used in so many different inventions. Or how in chemistry you combine different elements and suddenly you have completely different outcomes. Well, in this video I will show and explain you the most crucial nodes and will also tell you what you use them for most of the time. Some hotkeys I use in this video require Node Wrangler. It already ships with Blender, you just have to make sure it's activated by going into Blender's preferences under add-ons and making sure the checkbox next to Node Wrangler is ticked. Node Wrangler provides some hotkeys and features that will speed up your workflow in the shader editor. To get to the editor for the shader nodes, you can of course customize your Blender interface to show it, but for beginners it will probably be easier to just switch to the shading workspace. Don't get me wrong, you can also use these workspaces when you're not a beginner anymore. I also use them all the time. A shader defines the way how something reacts to light inside the render engine. For example, whether it is reflective, transparent, diffuse, or maybe it is a light source itself. So ultimately, a shader defines the look of a 3D model. You might already know the principled BSDF shader. It is Blender's default shader, and the idea behind the shader is being able to create any real-life material using only this shader. Also, it is optimized to fit PBR standards, so you can easily download textures, connect them to the shader, and have a realistic material. But sometimes you want to create a material that exceeds the limits of the principled BSDF shader, because it is either a very special material or something really stylized. Blender has a lot of different shaders, and you might already know some of their names from the principled BSDF shader. This is because the principled BSDF shader basically consists out of most of these shaders. By using these simpler shaders, you get more control over your material, and on top of that, you also benefit from a small performance boost since the shaders aren't as complex as the principled BSDF shader. Let's go over the most essential shaders. With the Glossy BSDF shader, you get a reflective material. It can be used on its own to create metal or a mirror, but it can also be used with other shaders to add reflections, which I will show you a bit later. The Diffuse shader is really plain and simple. It is useful if you want something to be influenced by lights and shadows without the color or texture of it being altered too much by the shader and the lighting. The transparent shader seems very simple and self-explaining, but it is very powerful nonetheless. It's mostly used to further modify other shaders by making them transparent. The Refraction shader is used to create the distortion from glass. So basically it's a shader that deforms everything you look at that's behind it. Very essential for creating glass, and on its own it can be used to create lenses from cameras or magnifying glasses. The Emission Shader is also very crucial. An emission object will act as a light source, so we can use it for creating lights, but it is also very useful for monitoring purposes, because it displays the color or texture that's used as an input for it without being influenced by other lights or shadows. So it can also be used for creating shadeless materials, which is crucial for many stylized shaders. Now, these two nodes are very special, since they allow you to combine shaders with each other. The difference between those two is that the add shader acts additive, so both shaders are added together to create a new shader from them. With the mix shader, you blend between two shaders, kinda like having one shader over the other and then changing the opacity with the factor slider. 0 would mean only the top input will be used, 1 would mean only the bottom input will be used, and 0.5 would mean both inputs would be used equally. Since the factor is an input, you can also use other nodes to control the value. This is where the Fresnel node comes in handy. It's used to blend between shaders based on the viewing angle. For example, if you look at the ocean and are far away of it, your view angle is rather flat and you will likely see the reflection of the ocean. But when you're standing inside the ocean and look directly down, you will likely be able to see through the water. Or imagine how you can see through a window or only see your reflection when looking at the glass from another angle. Well, if we combine a Glossy and a Refraction shader with the Fresnel node, we get exactly this effect. But it not only applies to materials you can look through. For example, if we switch the Refraction shader with a Diffuse shader, we get something that looks really close to plastic or some sort of glossy paint. This setup is crucial for what we call a dielectric material. Basically, it's everything that isn't metal. So wood, plastic, clay, paper, stucco, really pretty much everything that isn't out of metal. This is also why you have a metallic slider in the principled BSDF shader, because there are mostly metallic or non-metallic materials. Now let's combine some shaders together. Our goal is to create a glass material that is capable of doing a dispersion effect, which is this slight rainbow effect which you sometimes see on glass. We start by adding the fundamental nodes, which are 2 edge shader nodes and 3 refraction BSDF nodes. Now we connect them like this, so each shader will be added once. When we compare the outputs of a single refraction shader, the first edge shader node and the second edge shader node, we can see how our setup changes with each iteration of a refraction shader being added. As you can see, the result is getting brighter each time. To some extent, this is due to the input color of the shaders being white, and white plus white plus white equals a brighter white. Now, to create the rainbow effect, we will need multiple colors. And you might have been told a rainbow has 7 colors, but we don't need that many colors. Since a rainbow gets created by the scattering of light, we can recreate the effect by using the 3 main colors of light: red, green and blue. Make sure that each refraction shader is set to 100% of one of these colors. Now when these colors are being added together, we get the exact white we used as an input before, which is why our current output looks exactly like a single refraction shader from before. But when Blender is initializing the rendering, you can already see that the noise is more colorful than before, because the colors are really added to each other and then create the normal looking refraction as a result. Now if we play around with the IOR slider of each node so that none of them is the same, you can already see the dispersion effect happening. But it is very sharp and it isn't exactly a rainbow but 3 different colors. But we can blur these colors with each other to create a rainbow from them. To do so, we simply have to increase the roughness, which will scatter the light further so all 3 colors overlap with each other in different strengths, which creates a rainbow effect. I used a value node so I can use one slider to control all roughness inputs at once. But for it to probably look like glass, we will need to add reflections. And we can do so by using a mix shader node to mix our result with a glossy shader. And if you remember, we can now use the Fresnel node to get a proper looking result. It matters which shader is in the top input and which one is at the bottom, but you will likely figure out when you accidentally did it in the wrong order, because it will look weird then. So just swap the inputs if it looks weird. I created a beveled ring model to further display our material. And as you can see, it looks very pretty. And we only used 5 different nodes for that. And for the main rainbow effect, we only used 2 different types of nodes. So as you can see, it isn't really about having as many nodes as possible to make something look super complex, but it is rather about having a few building blocks and making the most out of them. And you can also apply this technique in other ways. For example, I've used this effect as a base for my free advanced glass shader, and then I will use this principle of using 3 colors to create a rainbow in order to create a DVD shader. You might have already noticed the volume output in Blender Shader Editor. But what can you do with it? Well, the surface shaders only affected the outer layer of the object. The volume shader will also make use of the inside. We have 3 volume shaders in Blender: the principled volume, the absorption volume and the scatter volume. The principled volume is a combination of both of these volume shaders and also comes with a few options which help integrating it with Blender's smoke and fire simulation. And this is one of the main uses of the volume shaders, controlling the look of gas materials like smoke. The volume scatter shader is widely used to mimic fog, dust and smoke. It's really useful to create dramatic lighting effects, as it will make light rays visible. Just think how you can make a laser pointer ray visible by pointing it through smoke. The volume absorption shader is absorbing light as it passes through an object. You mainly use it for water to create the effect that it gets darker the deeper you go, which is essential for setting the right feeling of an ocean. The other most common use case is to create colored glass. If we add a glass shader to the surface output and a volume absorption to the volume output, we can control the color of the glass by using the inputs of the volume absorption node to create realistic looking colored glass. Now that we went over the most relevant shaders, and before we dive into the procedural textures, I want to explain the different input and output sockets to you. You've probably already noticed that there are different colored sockets in Blender shader nodes. The green one is for shaders, the gray one is for values, the yellow one is for colors, and the purple one is for vectors. In many 3D softwares and render engines, you can only connect sockets with each other that have the same color. But Blender will automatically convert values, colors and vectors so you can use them interchangeably. The main difference between those input types is that values rely on a single channel, while the color and vector channels use 3 channels. The vector input uses a channel for each 3D axis, so X, Y, and Z. The color input uses a channel for each red, green, and blue, and additionally an alpha channel. So the colors actually use 4 channels, but for the conversions, the alpha channel will usually be ignored. So you can use them interchangeably without really using any data. But they give you info about what kind of input is expected. Now when you put a value into a color or vector input, Blender will use the value for all 3 channels. And when connecting a color output to a value input, the values of all 3 channels get merged. Keep in mind that the textures in Blender often provide a color and a vector output. You should use the output that has the same amount of channels as the input you want to connect it to, because this way your input doesn't need to be converted and it will give you a slightly better performance. A crucial thing to understand is that you can have multiple values for each channel. For example, when using a texture map, each pixel of the texture holds a value or multiple values depending on whether it is a grayscale texture or a texture in a RGB color space. How these values from the texture get applied depends on the projection of the texture. For example, you could use a UV map for projecting an image. But the key point is, you can get an increased amount of detail when using textures as inputs in comparison to a single float value. And where things get really interesting is when using procedural textures. These are textures that are generated within Blender itself. The advantages of that are that you can modify the parameters of the textures at any time, and the output also doesn't get pixelated and is seamless, as they are based on mathematical functions rather than a rasterized image like when using an image texture. To know when to use which procedural texture, I will again present you the most frequently used nodes. The noise texture is the most essential procedural texture, which is why you don't exclusively find it in Blender, but also in Photoshop, After Effects, DaVinci Resolve, Affinity Photo, GIMP, Houdini. Well, it is used everywhere. Some would even go so far to say that the whole VFX industry relies on noise textures. You use it everywhere where you need to add some sort of variation or randomness. And in nature, there is a lot of variation. So every time you want to make something look more interesting, or when something looks too flat or too consistent, you can use a noise texture to bring things to life. You can also use it when you want to randomize something. For this use case, the right noise texture of Blender is useful, as regular noise texture might be too interpolated at a lower scale. Which brings us to the most important input parameters of a noise texture. In many cases, you will be able to get away with only using the scale and the detail parameter. You can also choose different types of noise with this dropdown. I will explain the dimensions dropdown in a few minutes, but for the other parameters, I recommend you to read through the tooltips by hovering over the inputs or right-click the node and open the page of the online documentation about it to learn about more details. The wave texture is useful for creating directional patterns. So everywhere where you want something to follow a specific single direction, you will probably be able to achieve it with the wave texture. An example of this would be creating a procedural wood texture to mimic the grain of a wood. You can also set the wave texture to rings to get this kind of pattern. You might need to play around with the projections to recenter it. The default projection for all procedural textures in Blender is the generated projection, which is simply a 2D projection. You might have better luck with the object projection. It could be used to create ripples or to create the rings of a wood stump. You could also use it on a lamp to mimic window blinds. The most important inputs are the scale and the distortion parameters. The Voronoi texture is also very useful, as it creates a pattern with variation that still has identifiable structure. This can be used to recreate natural phenomena that feature organic variations but with sharp details. Examples would be rocks, caustics, or cracks in stone or glass. From the dropdown, you can change between different Voronoi patterns, while F1 and distance to edge are the most frequently used ones. As always, the scale parameter is the most relevant, but this time together with the randomness slider. With distance to edge and a low randomness, you can also create old, slightly scrambled tiles. The brick texture is useful for creating straight, man-made patterns. As the name already suggests, a common use case would be for bricks, but you can also customize it to create a grid. I always use it when I need to make something look structured or when making bricks or tiles. The gradient texture seems pretty self-explaining, but it has some quirks. From the drop-down, you can select different types of gradient progressions. A tricky but useful one is the spherical progression, because it won't be centered within your object. This happens because the coordinate input uses the corner of our object as a 0 point, while the gradient treats its own center point as its 0 point. Going from one corner to another is a distance of 1. So to recenter it, we will have to use half of this. So we use a mapping node to subtract 0.5 on all axes, and now the gradient is centered. The gradient is very useful to create masks and also to create blends of colors, of course. It's usually combined with the color ramp node to easily assign colors along the gradient. But the color ramp node is not only exclusively useful for the gradient texture, it's in fact one of the most frequently used nodes to further manipulate textures. Again, I will show you the most important nodes here. You can further adjust the appearance of textures by using nodes that will apply effects you might know from image manipulators like Photoshop, Affinity Photo or GIMP. This includes nodes like bright contrast, curves, gamma and the color ramp. Most of these effects are pretty self-explaining except for the color ramp. The color ramp will map your input from a scale of 0 to 1. And using the sliders from the color ramp, you can decide which color each value will be assigned to. For example, values of 0 or black will be assigned the color on the very left position. A value of 0.5 would become the color that's exactly in the center of the color ramp. Another very important node is the mix node. If it looks like this, when you add it, you will have to set it to color first. Using this node, you can mix two color inputs with each other by using different blend modes you might again know from other softwares. For example, this can be used to colorize a black and white texture. A very versatile node in Blender is the math node. It has many different mathematical operations and you might already know a lot of them from school. There is definitely a learning curve to getting the most out of math nodes, although some people are quick on picking it up. Most of the time I use a math node to multiply two inputs with each other or to make an input more or less intense by multiplying it accordingly. Something all texture nodes share is the vector input, and this is an opportunity for something extremely powerful, as you can change the mapping of the texture. The most common setup here is using a basic texture coordinate and mapping node. And now it's time for the magic. We add another procedural texture, for example a noise texture. Now we mix these nodes with each other using a mix color node and we set the blending from mix to linear light. Now when we play around with the factor slider and with the parameters of the noise node, you can see that we have just created a procedural displacement map for another procedural texture. So the output of this noise texture is now used to alter the positions where the other texture gets generated. And this is super crucial and powerful, as it allows us to further adjust the shape of a texture. Now let's talk about the dimensions of the procedural textures. When we use a Voronoi texture and plug it into the density of a volume scatter shader, we get this result. And there you can already see that the Voronoi texture has different values along three-dimensional axes. When we set the texture to 2D, we can see what it would look like with a two-dimensional input. But what about the 4D option? It's actually pretty simple. We get a new parameter called W, where we can control the evolution of the texture. To put it simple, the texture just travels without going into a specific direction. Now we will create another shader together, but this time we will heavily rely on using procedural textures. Ironically, we have to start with an image texture. Can be anything, but it will make things easier if it's in a square resolution so it won't get stretched. Our plan is to create a procedural shader that creates a mosaic out of every image. So just drag your image in there. And we will get right away to the main operator here, which is a Voronoi texture. And using the position output of the Voronoi texture, we get interesting vectors. Let's set the randomness to 0 to get a square grid. And then we plug it into the vector output of the image. And just like that, we've pixelated the image and we can control the density of the pixels with the scale of the Voronoi texture. The advantage of this method is that just like with real mosaic, each square uses only one color. Now I wanted to add gaps between each square. I tried doing it with a brick texture first, but after having issues with keeping it aligned to the mosaic, I decided to just use another Voronoi texture. This time we set it to distance to edge, which will give us a grid of beveled squares. I used the value node to control both scales at the same time, by the way. I used the mix color node and used a new Voronoi texture as a factor of it to mix the mosaic with black to create the gaps. With a color ramp, I could control how soft the fall off of the tiles is and how big the gaps are. The gaps looked a bit boring in pure black, so I used a noise texture with a very high scale to get some more detail in the gaps. I tried if displacing the noise with another Voronoi texture would look any good, but it didn't. I've put the Voronoi texture to the side as I liked it on its own and looked forward to using it later on. So I further customized the noise by using a color ramp. Then I've mixed the Voronoi texture with a mosaic and used the already existing noise texture to displace it. I did some further adjustments and then decided it's time to make it look like a proper material. So I added a principled BSDF shader and connected the color there. And using a color ramp, I was using the color to get a roughness map from it. To add a bit more depth to the material, we can manipulate the normals. The best fit would be a normal map here, but it was easier to just turn the color into a bump map. The difference is that a normal map fakes displacement in 3-dimensional axis and a bump map is grayscale, so it only gives information about the height. I've retouched the color ramp of the noise texture and added brown and green colors to mimic dirt and, I don't know, moss or something. Then I've connected the value that controls the scale to the scales of the remaining textures. And I kept the proportion by using a math node to multiply the input value by the result of a division between both scales, which gave me the correct value to keep the ratio. And we're done. I just want to also show you the displacement node, which enables you to displace the actual geometry instead of only faking it like a bump or normal map. But in order for it to work, you have to go into the material settings and under displacement set it to either displacement only or displacement and bump. Then we use the color as the input for the height of the displacement node and the output will be connected right here. You will most likely end up with a slightly deformed plane. This is because it really displaces the geometry. And in order for that to work, you need to have enough geometry. You can keep it non-destructively by using a subdivision surface modifier and setting it to simple. You can also do it destructively by going into edit mode and subdividing the plane. I checked the normalize option throughout the process of trying different things, which lead to some unexpected results. But yeah, it can give a better result, but it can also be harder to control as it's real geometry. I think in this case the bump map worked fine. You can also try to mix in some more noise textures for dirt and sand or whatever, so that's your optional homework task. Another useful node is the light path node. Most of the time it's used to control the visibility of a material. For example, you could create an emission material but want the object that acts as a light source to not be seen by the camera, while still keeping the light that it casts on other objects. You could also use it vice versa, for example if you want text to be only visible to the camera and to not be visible in reflections. With the shadow ray, you can also try to fake caustics by overshooting the brightness of a transparent shader. You could even use a Voronoi texture to increase this effect. Now I want to show you two more very powerful nodes. I am using Blender's Suzanne monkey for demonstration here. We start by adding a glossy shader. And now we get right to the twist. If we are an Eevee, we get access to the shader through RGB node. This will turn a shader into a texture basically, which means we can use it as a base for further processing steps. The shader to RGB node is commonly used to create cartoon or anime shaders. So let's create one together. We will add a color ramp node right after the shader to RGB node. It already looks kinda cool how the reflections turn grayscale, really makes a model pop somehow. But that's not what we're after. By setting the color ramp to constant, the input will only get mapped to the colors that are added as those markers without interpolation. So the output will only consist out of black and white right now. Now let me turn off the HDRI and add a lamp to get a better view of what's happening here. I will also increase the roughness of the glossy shader so the input for the color ramp is softened instead of only having a few tiny highlights from the lamp. I will change the black to a slightly dark grey and also add another slightly brighter grey. And when I further adjust the lamp, you will already see the cartoon shading effect. Now by adding a mix color node and setting it to multiply, we can easily colorize the shader while maintaining the shading. Now we will add an ambient occlusion node. The output of it gives us a map of contact shadows within the model. We will add a color ramp again and set it to constant to make it fit the current art style. Now we duplicate the color mix node, which is set to multiply, and put the ambient occlusion onto our prior result. Now we have even more shadows showcasing the shape of our model. If you plan on using the setup among other projects or sharing it online, you can use a node group to kinda build a custom interface for your shader. We start by selecting all of our nodes and pressing Ctrl G to put them all into a node group. Now we connect every value we want to be changeable. Sadly, we can't add inputs that control the settings of our color ramp. When you press N, you can expand this menu where you can rename the inputs, and you can also set custom limits for them. I switched up the inputs of the color mix node here, so the factor controls the intensity of the shading rather than the intensity of the color. You can enter and exit the node group anytime by pressing Tab. Let's finish things up by setting a name for the node group and assigning the color to it that indicates that it's a shader node. You can also use the description inputs here to enter custom tooltips that appear when hovering over the name of the shader or over each value. To use this node group, you should of course save the .blend file, and then when in another file, you can either use the append feature of Blender or you could utilize Blender's asset browser. If you found this video helpful, it would be nice if you would also help me by subscribing to this channel.